I want to continue our discussion of normal subgroups and kernels of homomorphisms. So we've seen already in Theorem 3 of section 3.1 that if you have a homomorphism phi from a group G to a group H, and the kernel of that homomorphism is K, then you can put a group structure on the set of left cosets of K in G by defining the operation UK, the coset of K containing U, times VK equals UVK. And this operation is well defined, and this set with this operation forms a group, which we've been calling a factor group or quotient group. Okay, so we've also seen that if you start with any subgroup N, and you try to put an operation on the set of left cosets of N and G by saying that the left coset of N containing U times the left coset of N containing V is the left coset of N containing U times V, then this operation is well defined if and only if N is a normal subgroup of G. So you can define this quotient group, factor group, whenever you have a normal subgroup or whenever you have the kernel of a homomorphism. So this is kind of a roundabout way of saying, well, this proposition and this theorem together show that the kernel of any homomorphism has to be a normal subgroup. So let me point out that you could also prove this directly, like from the definition of the kernel of a homomorphism. You can also use this proposition that we proved last time, where you wrote down the cosets of a subgroup of G given by the kernel of a homomorphism, and you saw that the left coset of the kernel containing U is the same as the right coset of the kernel containing U. Both of those cosets are equal to the fiber of phi above phi of U. So left cosets are equal to right cosets because they're both equal to a fiber. Okay, so left cosets are right cosets. That's one of the equivalent criteria of saying that a subgroup is normal. So this also shows that the kernel of phi is a normal subgroup of G. Okay, so this proposition now puts us in this case, in this situation where we know that anytime we have a normal subgroup, we can define a quotient group. And we know that one way to get a normal subgroup is to take the kernel of any homomorphism. The proposition I want to start with says that that's it, that the only way to get a normal subgroup is by taking the kernel of some homomorphism. That N is normal in G if and only if N is equal to the kernel of phi for some homomorphism phi from G to some group H. So the set of normal subgroups is exactly the set of subgroups that occur as the kernel of some homomorphism. So we've already seen one direction of this, that if N is the kernel of a homomorphism, then N is normal in G. So what we have to do is prove the other direction, say that if you start with a normal subgroup, it is the kernel of some homomorphism. And the way that we're going to do that is we're just going to write that homomorphism down. So I'll pause and erase and say something about the proof. So we want to prove this proposition that a subgroup is normal if and only if it occurs as the kernel of some homomorphism. As we just said, we've already done one direction. If you're the kernel of a homomorphism, then you're normal. So let's suppose we start with a normal subgroup of G. We're going to construct a homomorphism phi from G to H so that N is exactly the kernel. So what is H going to be? It's going to be the quotient group G mod N. And we know that that is a group because N is normal. So we can put this group structure on the set of left cosets of N in G. So what's our homomorphism going to be? It's going to be this map that takes G to G mod N. And we're going to take pi of little g will be the left coset of N containing G. So this is the big idea in this proof. But this is a very natural kind of homomorphism function to try to write down. We're just sending the element little g to the left coset of N containing that element. So what do we have to do? We have to show that pi is a homomorphism, and we have to note, if we know it's a homomorphism, that the kernel of pi is equal to N. Well, that second part is totally clear. that the left coset of n containing G is the left coset of n containing 1, the identity, if and only if G is actually in n. So the kernel part is easy. And all we have to do now is show that pi is a homomorphism. So what do we need? We need pi of G1 times G2 to be equal to pi of G1 times pi of G2. So let's just start with one side and see what we get. OK, so what is pi of G1, G2? Well, it's the left coset of n containing G1, G2. But then, by the definition of the operation, let me say definition of the group operation in the right-hand side in G mod n, this is the left coset of n containing G1 times the left coset of n containing G2. So this is just because we know that the right-hand side is a group with this operation. And now that is pi G1 times pi G2. And we're done with the proof that pi is a homomorphism. And then we already said that once you know it's a homomorphism, it is clear that the kernel is equal to n. So that's the end of the proof that the normal subgroups are exactly the ones that come from the kernel of a homomorphism. So one more thing that I want to say about this proof is that the homomorphism here gets a name. So this homomorphism, let's say pi from G to G mod n, where n is a normal subgroup, is called the natural projection of G onto G mod n. So why is that? We're taking an element of G and sending it to the corresponding coset of G mod n. G mod n is a smaller group than G. Like many elements of G are bundled together in the same coset of n. So we're taking like a bigger thing and projecting it down onto a smaller thing. So I'll pause and erase, and then we'll talk about some examples having to do with normal subgroups. Let's talk a little more about examples of normal subgroups and quotients. So we've already seen that every subgroup of an abelian group is normal. It's normal because Gn G inverse is always equal to n for any G and any n. So if you look at the subgroup n, G times that subgroup times G inverse will be that subgroup because every element gets fixed. So what does that mean? Inside an abelian group, you can take the quotient by any subgroup. In particular, cyclic groups are abelian, so you can take the quotient by any subgroup. And we already proved that subgroups of cyclic groups are also cyclic. So what do those quotients look like? And we're going to prove that quotient groups of cyclic groups are cyclic. And lots of arguments with cyclic groups are easier if you use the fact that any infinite cyclic group is isomorphic to Z, and any finite cyclic group of order n is isomorphic to Z mod nz. So there's a full proof of that in Dummett and Foote. I encourage you to look it up, but you can also think about how to write down a proof by actually just writing down an isomorphism from your chosen infinite cyclic group to Z. Like, what is it that you want to send to 1? OK, so let's assume that we have this result. So let's do the infinite case first. So we have G is isomorphic to Z. All the subgroups of Z, subgroups are cyclic also. So they look like nz for some n greater than or equal to 1, or the trivial subgroup. The quotient of a cyclic group, the quotient of any group by the trivial subgroup is the group itself. And so G mod the trivial subgroup is isomorphic to G, which is cyclic. So then we just have to note that if we take any of the other subgroups, and we take Z quotient by NZ, what we're getting is the finite cyclic group Z mod NZ, and that is cyclic. So now let's do the case where G is a finite cyclic group of order n, so it's isomorphic to Z mod NZ. We've seen that there's a bijection between subgroups of Z mod NZ and divisors D of n. Every subgroup of G is of the form cyclic subgroup generated by x to the d for some d dividing n. So in general, what is this set of left cosets? G mod n, well, it's everything that can be written as G times n for some element G in G, but lots of them are going to be the same. Like this is the set, but this doesn't give you a description of the distinct left cosets. If you just translate into what this means for a cyclic group, this is the set of all the left cosets that are of the form x to some power times n, where that power runs through the elements of Z. And now you can note that the left coset of n containing x to the alpha is the same as the left coset of n containing x multiplied by itself alpha times, just by the definition of the group operation in G mod n. So what does that mean? So G mod n is isomorphic to the cyclic subgroup generated by, or it is the cyclic group generated by the single coset x times n. So every other coset is some power of this one coset. So in this particular case, where we have a finite cyclic group of order n, what do these sets of cosets look like? Well, we have n itself, the left coset of n containing x to the 1, up to the left coset of n containing x to the d minus 1. So we have these d distinct left cosets. So let me just say something about the order of the groups here. If n is the subgroup generated by x to the d, well, what's the order of that? It's the smallest power that you raise x to the d to get back to 1, and that is n over d. So this subgroup has order n over d. And we saw that there are these d distinct left cosets. So the order of the quotient group is d. But that is n over d, which is the size of the group G divided by the size of the subgroup n. And what we're going to see is this relation is going to hold in general. So I'm going to pause and erase, and I want to do one last kind of example of a normal subgroup. So as a final example here, let's take a subgroup contained in the center of a group. So I claim that this is always normal. And the reason that this is normal is the same reason that subgroups of abelian groups are normal. Because if you take G, n, G inverse, where n is something in your subgroup contained in the center, then that means n commutes with everything. So you can switch the order of n and G inverse, and you get G inverse n, and you just get n. So not only is G times this subgroup times G inverse equal to the subgroup, that it's fixed when you conjugate by G, but it fixes every element. So it's exactly the same thing that was happening with subgroups of abelian groups. So one way to say it is that the normalizer of this subgroup is the entire group, or this subgroup of the center is normal. If you just take n to be the center itself, we can see that the center of a group is always a normal subgroup.